Picture yourself in a pitch-black room. You hold up a simple wooden stick and flick on a flashlight. Instantly, a shadow is cast. If you move your hand even slightly, tilting the beam up or stepping backward, that shadow warps. It stretches out into a long distortion or shrinks down to a nub. The shadow is real, but its shape is entirely dependent on your perspective. If you handed that exact silhouette to an engineer to manufacture a replica, they couldn't do it. A flashlight creates perspective. Its light rays radiate outward from a single point, projecting a shadow physically larger than the object itself. To accurately communicate the exact shape of an object, we have to find a way to flatten three-dimensional space onto a two-dimensional sheet of paper, preserving the precise mathematical measurements along the way. The solution to this distortion is a thought experiment of its own. We have to swap our flashlight for a light source that emits rays that never spread out, traveling instead in perfectly parallel lines. This flowchart shows the taxonomy of how we project images. On the right, we have standard perspective drawing, where lines of sight converge. But the system on the left branches into parallel, orthogonal projections. By utilizing those parallel lines of sight, we remove perspective entirely. That strict mathematical rule turns a loose sketch into an exact blueprint. When parallel light rays hit an object, they cast a shadow that matches its exact silhouette at a precise 1-to-1 scale. But a single shadow creates ambiguity. A 3D sphere and a flat 2D cylinder will project the exact same flat circle. To solve this ambiguity, we place the object inside a conceptual glass box. We keep the wall to catch the front profile, the vertical plane, or VP, and we add a floor beneath it to catch the shadow from above, the horizontal plane, or HP. Because these two planes are infinitely long, they intersect and slice space into 4 distinct zones. We call these the 4 quadrants. By illuminating the object from the front and from the top simultaneously, we capture 2 separate angles. Those dual shadows lock in the complete 3-dimensional identity of the object. We suspend a simple line segment in the upper right zone, the first quadrant. A horizontal line beam projects a shadow onto the vertical plane, forming the front view. A second beam from above casts a shadow onto the horizontal plane, forming the top view. We now have a full record of the line's dimensions. However, this data is currently suspended across 2 different planes inside an intersecting 3-dimensional glass box, which is impossible to print in an engineering manual. To make this information useful, engineers follow a universal convention to unfold that spatial geometry onto a flat sheet of paper. There is a strict rule for this process. The horizontal plane must always rotate exactly 90 degrees clockwise. This motion hinges the floor downward until it aligns perfectly flush with the vertical plane. A projected shadow only captures the actual, measurable length of a line if it sits perfectly parallel to the projection wall. We call this true length. But if the object tilts away, the shadow compresses, creating a shorter apparent length. Recognizing that angle of inclination is how we determine if a drawing shows the physical dimensions of a part, or if we are looking at a foreshortened view. What remains after unfolding the planes is a flat page intersected by a single horizontal reference, the XY axis line. This axis distinctly separates the front view shadow from the top view shadow. This image illustrates a block residing entirely in the bottom left third quadrant. An engineer reading this schematic knows exactly where the object sits in space, because a third quadrant projection arranges the top and front views entirely differently than one placed in the first quadrant. An orthographic projection does not rely on artistic interpretation. It functions entirely as a rigorous mathematical code built upon the behavior of light and spatial rotation. The ultimate utility of this system is that it functions flawlessly in reverse. By starting with nothing but a set of flat shadows and applying the geometric rules of inclination, we can calculate the exact dimensions required to reconstruct complex physical forms. A 2-dimensional schematic seamlessly inflates, extruding off the page to become a dense, tangible object with perfect manufacturing tolerances. Engineering drawings utilize intersecting planes and strictly controlled light to capture the dimensions of space. They give us the precise language needed to reverse engineer reality itself.